Welcome to another soothing journey through the cosmos. This is Science to Sleep By, where knowledge becomes comfort, and the mysteries of the universe unfold gently as you drift into rest. Tonight, we'll float across the Milky Way, our home galaxy, and compare it to the titans of the cosmos, colossal galaxies so vast they defy imagination. We'll explore what makes our galaxy special, what lies beyond it, and how we fit within the grand architecture of the universe. So, take a deep breath. Let the stars calm your mind, and let's begin our journey from the familiar arms of the Milky Way to the unimaginable scales of the largest galaxies known to science. Close your eyes for a moment and imagine a slow rotation of starlight, drifting quietly through the endless black sea of space. This is our home, the Milky Way galaxy, a vast, spiraling island of stars, glowing softly in the silent night of the cosmos. Every point of light you see in the night sky is one of its residents, and yet, what we can see with our eyes is only a fragile glimpse of its full grandeur. The Milky Way stretches about 100,000 light-years across a distance so immense that even if you could travel at the speed of light, it would take 100,000 years just to go from one end to the other. It is a structure that contains somewhere between 200 and 400 billion stars, and likely even more planets, nebulae, clusters, and clouds of interstellar gas. It is more than just a collection of stars. It is a dynamic, breathing entity of cosmic evolution, a place where new stars are born, old stars die, and elements are forged in the crucible of time. If you were to rise above the galactic plane and look down upon the Milky Way from afar, you would see a glowing whirlpool of light, its arms spiraling outward from a bright, central core. Astronomers call this a barred spiral galaxy because of the elongated bar-like structure of stars that runs through its center, feeding material into its nucleus and shaping the pattern of its majestic arms. These arms are not static, they rotate, they twist, and they carry along with them vast molecular clouds where stars are born. The Milky Way is not fixed in time. It moves, it changes, and it evolves. It has been doing so for more than 13 billion years. Our solar system lies quietly within one of those arms, the Orion Arm, which is a smaller spur between two of the Milky Way's major arms, the Sagittarius and Perseus arms. From our vantage point, we are located about 27,000 light-years from the galactic center, in a relatively calm and safe region. It is far enough from the violent activity of the core to avoid dangerous radiation bursts, yet close enough to witness the gentle glow of our galaxy's heart. Here, among billions of stars, our sun orbits the galactic center once every 230 million years. It's a slow, graceful dance, a journey our planet has taken roughly 20 times since its formation. At the heart of our galaxy lies something extraordinary, an invisible powerhouse known as Sagittarius A. A supermassive black hole with a mass equivalent to about 4 million suns. It sits in the dense core of the Milky Way, pulling on stars, dust, and gas with its immense gravity. Surrounding it is a region teeming with activity, stars that whip around the black hole at incredible speeds, massive clouds of gas being heated to millions of degrees, and magnetic fields, weaving patterns of unseen power. Sagittarius is quiet now, but it has not always been. Astronomers have found evidence that, long ago, it may have been much more active, feeding on material and releasing bursts of radiation that echoed across the galaxy. The Milky Way's disk is filled with a variety of environments, star-forming regions glowing in soft pink light, ancient clusters of stars orbiting like celestial archives, and lanes of dark dust tracing the spiral arms like delicate shadows. When we look up at the night sky from a dark location on Earth, we see a milky band stretching across the heavens that's the edge-on view of our galaxy's disk. The ancient Greeks thought it was a river of milk spilled by the gods, hence the name Milky Way. But what we see as a faint glow is actually the combined light of billions of distant stars, too faint to be resolved individually. Each one adds its own small whisper of light to that glowing band, forming a collective chorus of starlight. The Milky Way is surrounded by a vast halo, a spherical region that extends far beyond its visible disk. This halo contains old stars, globular clusters, and most importantly, dark matter. Dark matter makes up the majority of the galaxy's mass, even though we cannot see it or directly detect it. We only know it exists because of its gravitational influence. It is the invisible framework that holds the galaxy together, preventing it from spinning apart. Without dark matter, the Milky Way could not exist in its current form. This hidden skeleton of the cosmos extends well beyond the edges of visible stars, shaping the way the galaxy rotates and interacts with its neighbors. Speaking of neighbors, the Milky Way is not alone in the cosmos. It is part of a small family of galaxies known as the Local Group, a community that includes the Andromeda Galaxy, the Triangulum Galaxy, and dozens of smaller dwarf galaxies that orbit them like satellites. These neighboring galaxies are bound together by gravity, slowly drifting toward one another over billions of years. In fact, Andromeda and the Milky Way are on a collision course. In about 4 billion years, they will merge, forming a new, larger galaxy. But even now, they share a subtle gravitational bond, influencing each other's structure in ways we are only beginning to understand. Inside our galaxy, stars of all ages coexist. There are newborns, bright, blue giants that burn intensely, but live short lives of only a few million years. There are middle-aged stars like our Sun, shining steadily for billions of years. And there are the elders, ancient red dwarfs and white dwarfs, remnants of stars that formed shortly after the galaxy itself was born. This diversity of stellar life tells the story of our galaxy's evolution. Each star is like a word in a grand cosmic novel, and together, they narrate billions of years of creation, destruction, and rebirth. Between these stars floats the interstellar medium, a thin mix of gas and dust that fills the spaces between solar systems. Though it seems empty, it is the birthplace of stars. Gravity slowly gathers this material into dense clouds, which collapse under their own weight, forming new suns and new worlds. These newborn stars illuminate their birth clouds, creating beautiful nebulae that glow in soft blues and pinks. The Milky Way is alive with this quiet cycle of creation, a process that has continued without pause since the galaxy's earliest days. Our galaxy also serves as a cosmic archive, preserving the chemical history of the universe. The first generation of stars, formed from pure hydrogen and helium, created heavier elements in their cores, carbon, oxygen, iron, then scattered them into space through supernova explosions. Those materials became the building blocks of the next generation of stars, and eventually, the planets and us. Every atom of carbon in your body was once forged in a star that lived and died long before the sun was born. The Milky Way is not just a home of stars, it is a factory of life, a forge of elements that makes existence itself possible. If we could step back far enough, the Milky Way would appear as a shimmering disk of light, surrounded by faint halos and dotted with smaller companion galaxies. Its spiral arms would glimmer softly, each one a river of starlight stretching across the dark. Yet even with all its majesty, the Milky Way is just one galaxy among trillions. It's easy to feel small in that realization, but there's also something profoundly comforting in it. Because within this grand cosmic expanse, we have found our place. We orbit a gentle star within a quiet arm of a beautiful galaxy, in a universe that continues to evolve, expand, and inspire us to look upward, to wonder, and to dream. The Milky Way is not merely a collection of stars scattered randomly through space. It is a masterpiece of structure, symmetry, and motion. Every curve of its spiral arms, every glowing cloud of gas, and every dark dust lane weaving between them, tells a story written across billions of years. To truly understand the Milky Way, one must imagine it not as a flat image in a textbook, but as a vast, living system, a galaxy breathing slowly, turning majestically, and evolving under the quiet laws of gravity. Its beauty is not only in what we see, but in the order hidden within the chaos, the rhythm that ties together light, matter, and time itself. At the heart of this enormous galactic system lies its most radiant feature, the central bulge. This region forms the glowing core of the Milky Way, a densely packed sphere of stars that shines with a golden light. It is here that the oldest stars in our galaxy reside, ancient suns that were born when the Milky Way itself was still taking shape. The bulge is thick with starlight, and at its very center, hidden behind curtains of dust, is the supermassive black hole known as Sagittarius A. Around this central darkness, millions of stars orbit at dizzying speeds, each one caught in the gravitational embrace of the galaxy's invisible heart. If we could see the galactic center in infrared or radio wavelengths, the view would be breathtaking. Clusters of hot young stars, streams of gas spiraling inward, and shockwaves of energy rippling outward from unseen forces. The core is a paradox. It is both the calm center of the Milky Way and its most turbulent region. Radiating outward from this luminous heart are the spiral arms, those iconic, graceful arcs of light that define the Milky Way's beauty. These arms are not solid structures, but patterns of density like waves in the ocean. Stars and clouds of gas move through them, drawn together by the gravitational tides of the galaxy's rotation. As interstellar gas enters a spiral arm, it is compressed, triggering bursts of star formation. The youngest, brightest, and bluest stars light up the arms like cosmic lanterns, giving the Milky Way its distinctive spiral glow. These arms rotate slowly, each completing a turn roughly every few 100 million years. The entire disk of the galaxy spins like a vast celestial record, with stars near the center moving faster than those in the outer regions, all bound by the unseen hand of dark matter that shapes their motion. Our solar system resides in a relatively quiet region between two of the major arms, in what astronomers call the Orion Arm, or sometimes the Orion Spur. This is not one of the grand, sweeping arms that define the Milky Way's full spiral pattern, but rather a smaller, connecting segment, a kind of inter-arm bridge between the Sagittarius and Perseus arms. It's a peaceful corner of the galaxy, far enough from the dangerous radiation and gravitational chaos of the core to allow life to thrive. From here, our sun orbits the galactic center at a speed of about 514,000 miles per hour, completing one full revolution roughly every 230 million years. It's a journey so vast that in all of Earth's history, since the first dinosaurs appeared, our planet has completed only a single galactic year. Surrounding these bright arms is the galactic disk, a vast, thin layer of stars, gas, and dust, stretching across 100,000 light years. The disk is where most of the Milky Way's visible material resides, and within it lie the birthplaces of new star regions known as stellar nurseries or nebulae. The Orion Nebula, for example, located in our own arm, is a stellar nursery visible even from Earth through small telescopes. Inside such regions, cold clouds of hydrogen gas collapse under their own gravity, igniting nuclear fusion and creating new suns. The Milky Way constantly recycles its material, turning old stars into new ones, transforming the ashes of the past into the light of the future. Threading through this disk are lanes of dark interstellar dust. These dense clouds of carbon, silicon, and ice particles block visible light, giving the Milky Way its mottled, textured appearance when viewed from Earth. Yet these dark regions are not voids, they are the seeds of future stars, the raw material of creation. When we look up at the Milky Way on a moonless night, those dark rifts and bands are the silhouettes of these clouds, casting shadows against the glow of billions of distant stars. The interplay of light and darkness across the galactic plane gives the Milky Way a beauty that feels almost organic, like the veins of a living organism pulsing with cosmic energy. Beyond the disk lies another component of the Milky Way's structure, the thick disk and the halo. The thick disk contains older stars and globular clusters, ancient relics that orbit above and below the galactic plane. These clusters are among the oldest known objects in the universe, some dating back nearly to the dawn of time. Each globular cluster contains hundreds of thousands of tightly bound stars, orbiting together like glowing beehives in the night. Surrounding the galaxy entirely is the stellar halo, a vast, faint sphere that extends far beyond the visible disk. It is populated by old stars, scattered remnants of smaller galaxies that the Milky Way absorbed long ago. This halo is also where most of the galaxy's dark matter resides, forming a kind of invisible scaffold that holds the entire structure together. Without this dark framework, the galaxy's rotation would tear it apart. The Milky Way's architecture is more than physical, it's dynamic. Every component is in motion, following its own rhythm in the great cosmic symphony. Stars in the inner regions orbit faster, while those farther out move more slowly, but all are connected by the gravitational harmony of the whole. The spiral arms themselves are constantly shifting, fading, and reforming over cosmic time. They are not permanent fixtures, but patterns of density that move through the disk, like ripples through water. Even the galaxy's shape is not perfectly flat, it's warped, slightly twisted by gravitational interactions with neighboring galaxies, such as the Large and Small Magellanic Clouds, two dwarf companions orbiting our own. These smaller galaxies tug at the Milky Way, distorting its outer regions and adding to its graceful complexity. When astronomers map the Milky Way using different wavelengths of light, they uncover its hidden dimensions. In visible light, we see stars and dust. In infrared, we can peer through the dust to glimpse the heart of the galaxy. In radio waves, we trace the cold hydrogen gas that outlines the spiral arms. And in X-rays, we observe energetic phenomena like supernova remnants and black hole activity. Each wavelength reveals another layer of the Milky Way structure, as if peeling back veils to reveal the depth of its design. From all these observations, a picture emerges of a galaxy that is both orderly and dynamic, vast yet finely balanced. Even within this complexity, the Milky Way's beauty remains undeniable. Its light, soft and ancient, reaches us across unimaginable distances. Every star within it is a point of history, a testament to the enduring cycle of cosmic creation. The geometry of its arms, the radiant bulge at its core, the halo that surrounds it like a faint aura, all of it works together to create something both immense and intimate. When we see the Milky Way stretched across the sky, we are not looking outward, we are looking inward, into the very structure that holds our world, our sun, and our lives in place. Its spiraling symmetry connects us to the universe in a way words can barely describe. The Milky Way structure tells us that beauty in the universe is not random, it emerges from balance, from motion, from the quiet persistence of gravity shaping light over time. From the blazing core to the delicate arcs of its arms, from the dust-filled lanes to the distant halo of forgotten stars, every layer of this galaxy is part of a greater whole. It is both ancient and alive, shaped by forces that act slowly yet with purpose, building and rebuilding across eons. And as our tiny world circles the sun, within one of its gentle arms, we remain part of this grand architecture, participants in the elegant design of the galaxy we call home. As magnificent as the Milky Way appears when we look up at the night sky, it is, in the grand scheme of the cosmos, a middleweight, a beautifully structured but modest galaxy when compared to the true titans of the universe. Beyond the soft spiral arms of our home, a realm dominated by galaxies so vast and so luminous that they challenge our imagination. These colossal systems are not just collections of stars. They are the ancient monarchs of the cosmos, formed through endless collisions and mergers, growing ever larger over billions of years. Their light has traveled across immense stretches of space to reach us, whispering stories of creation, violence, and transformation on scales we can barely comprehend. The universe is a tapestry of galaxies, each one a different shape, size, and age. Some are small and irregular, others are spiraled like the Milky Way, and then there are the elliptical giants, massive, glowing orbs of stars that can stretch millions of light years across. These are the behemoths, the gravitational centers of galaxy clusters, and the heavyweights of the cosmos. While spiral galaxies like ours are known for their graceful beauty, elliptical galaxies are known for their mass, their sheer density of stars, and their dominance in the cosmic landscape. Their structures are smoother, lacking the organized spiral arms that define galaxies like the Milky Way. Instead, they appear as enormous, luminous spheres, with stars distributed evenly throughout. creating a glowing sea of light that fades gradually into the darkness of space. The formation of these giants is a story written in collisions. When galaxies merge, their shapes distort, their stars intermingle, and their gas clouds collide and compress, igniting bursts of star formation. Over time, after multiple mergers, the resulting system loses its spiral structure and transforms into a vast elliptical shape. The more galaxies that combine, the more massive and diffuse the final product becomes. These mergers are not sudden cataclysms, but slow, gravitational dances that unfold over hundreds of millions of years. During such events, stars rarely collide directly. Space within galaxies is mostly empty, but the gravitational interactions create immense tidal forces that reshape everything. Clouds of gas are torn apart, new stars are born, and black holes at galactic centers grow larger as they devour surrounding material. The largest galaxies are usually found at the centers of galaxy clusters, the cosmic cities, where hundreds or even thousands of galaxies are bound together by gravity. At the heart of these clusters lies a single, dominant galaxy known as a CD galaxy, a giant elliptical that reigns over its surroundings like a monarch in a vast empire. These central galaxies have grown fat on a steady diet of smaller companions, absorbing them one by one. The process is sometimes described as galactic cannibalism, an apt metaphor for the way cosmic evolution proceeds through both creation and consumption. Over billions of years, these giants have become reservoirs of ancient starlight, containing trillions of stars and weighing up to 100 times more than the Milky Way. Among the known giants, one name often rises above the rest: IC 1101, discovered in the 1980s. This galaxy resides in the Able 2029 galaxy cluster, roughly a billion light-years away in the constellation Virgo. It is often cited as the largest known galaxy in the observable universe, a behemoth that stretches more than 5.5 million light-years across. To imagine that scale, consider this: if the Milky Way were the size of a dinner plate, IC 1101 would be a field stretching across an entire city. It contains perhaps 100 trillion stars, hundreds of times more than our galaxy, and its central region glows with an intensity that outshines entire galactic groups. The gravitational field of such a galaxy is so vast that even nearby galaxies within the cluster orbit around it, bound by its immense mass. But IC 1101 is not alone in this category of cosmic leviathans. Other giants like Alcyone, a massive radio galaxy with lobes extending over 16 million light-years, or NGC 4874 and NGC 4889 in the Coma cluster, also stand as testaments to the incredible diversity of galactic evolution. These galaxies emit powerful streams of radio waves, jets of charged particles accelerated by their supermassive black holes, which can be billions of times the mass of our Sun. In some cases, these jets extend far beyond the visible edges of the galaxies themselves, painting the intergalactic medium with streaks of invisible energy. The scale of these systems defies intuition. Their stars are spread across distances so vast that even light takes millions of years to cross from one side to the other. And yet, their gravity binds them into coherent, stable structures. These galactic behemoths are relics of an earlier universe, formed when the cosmos was denser, more chaotic, and filled with more gas. Over time, as smaller galaxies collided and merged, the giants grew, becoming brighter and more massive. Yet, paradoxically, most of the stars in these giant ellipticals are old and red, their star-forming material long since exhausted. They glow with the collective light of ancient suns, each one quietly aging, adding to the galaxy's warm, diffuse radiance. These galaxies are often described as red and dead, no longer forming new stars, but still radiating the combined glow of countless old ones. In contrast, the Milky Way is still alive, its spiral arms rich with gas and dust that continue to create new generations of stars. In this way, our galaxy is younger, more dynamic, while the giant ellipticals are the ancient elders of the cosmic community, massive, wise, but past their most active years, their centers, however, tell a different story. Deep within these galaxies reside some of the largest black holes ever discovered, monsters whose masses can exceed 10 billion suns. These supermassive black holes act like engines of energy, occasionally feeding on surrounding gas and dust, releasing tremendous amounts of radiation. In the early universe, when these giants were still growing, such black holes may have powered quasars, blinding beacons of light visible across billions of light years. Today, many of these central black holes have quieted, but they remain as powerful gravitational anchors, stabilizing their galaxies and influencing their evolution. In some galaxies, we can still detect faint traces of past outbursts, radio lobes, shockwaves, and X-ray emissions that remind us of the energy these cosmic titans once unleashed. The existence of such enormous galaxies raises profound questions about the nature of the universe itself. How could structures so vast form in a universe governed by simple physical laws? The answer lies in the long, slow process of cosmic evolution. In the early universe, small fluctuations in density caused matter to clump together under gravity. Over time, these clumps merged to form galaxies, and galaxies merged to form clusters. The largest galaxies grew in the densest regions of space, where gravity pulled everything inward. Each merger added to their size, and each generation of stars added to their luminosity. The process is still ongoing today, though at a slower pace, as the universe expands and galaxies drift farther apart. From our perspective, these galactic giants remind us of the scale of creation. The Milky Way, with its 100 billion stars, seems immense when viewed from within, but compared to the largest ellipticals, it is merely one spark in a vast constellation of galactic light. These behemoths dominate their clusters, shaping the flow of matter and energy across millions of light years. Their gravity bends space-time, their radiation fills the void, and their histories trace the evolution of the universe itself. To study them is to glimpse the full power of cosmic growth, the way gravity, over unimaginable timescales, can build structures that defy comprehension. When astronomers look at these giants through powerful telescopes, they are seeing not just light, but time itself. The glow that reaches our instruments began its journey a billion years ago or more, carrying the record of ancient stars and long-forgotten collisions. Each photon that enters a telescope's lens is a messenger from an age when the universe was younger, denser, and bursting with creation. The largest galaxies are like fossils of the cosmos, preserving within their vast forms the memory of the universe's most dramatic events. They stand as both monuments to what the cosmos once was and blueprints of what it might become. The galactic behemoths, in their silence and size, speak to the immensity of the universe and the unyielding power of gravity. They are the architects of cosmic scale, built through destruction, molded through time, and shining with the accumulated light of countless generations of stars. While the Milky Way moves gracefully through the local group, these giants command entire clusters, shaping the flow of galaxies around them, dictating the rhythm of cosmic evolution with their presence alone. Their grandeur is a reminder that in the universe, beauty and power often coexist, that order arises from chaos, and that even the most massive creations began from small, quiet beginnings, aiming the countless galaxies scattered through the visible universe. There exists one so immense, so breathtakingly vast, that it pushes the limits of what we can imagine a galaxy to be. Its name is IC 1101, and it stands as the largest known galaxy ever discovered by astronomers, a cosmic leviathan that humbles even the mighty Milky Way, situated roughly 1 billion light-years away from Earth in the constellation of Virgo. IC 1101 resides at the core of the Able 2029 Galaxy Cluster, a colossal congregation of galaxies bound together by gravity. It is here, in this dense and ancient region of space, that IC 1101 dominates, reigning as the luminous centerpiece of its cluster, a silent monarch surrounded by a court of lesser galaxies. To understand IC 1101 is to confront the vastness of creation itself. This galaxy is estimated to span more than 5.5 million light-years in diameter. For comparison, the Milky Way stretches about 100,000 light-years across, meaning that IC 1101 is roughly 55 times wider. If our galaxy were reduced to the size of a coin, IC 1101 would be the size of a large dinner table. Even light, traveling at nearly 186,000 miles per second, would take over 5 million years to travel from one edge of IC 1101 to the other. This staggering size makes it not just the largest known galaxy, but one of the largest coherent structures ever observed that can still be called a single galaxy rather than a cluster. IC 1101E's brilliance is equally astounding. It contains an estimated 100 trillion stars, about 1,000 times more than the Milky Way's 200 to 400 billion. These stars bathe the galaxy in a diffuse golden glow, a warm, ancient light that suggests a population dominated by old, evolved suns. Unlike the bright blue stars found in the spiral arms of galaxies like ours, IC 1101E stars are mostly aged and reddish, marking it as an old elliptical galaxy whose star-forming days are largely behind it. The galaxy's light shines across millions of light-years, its soft halo gradually fading into the blackness of space. It has no distinct spiral arms, no clear structure, only a smooth, luminous gradient of starlight, stretching outward like a cosmic fog of gold and amber. Its colossal size did not arise by chance. IC 1101 is the product of countless mergers, galactic collisions that occurred over billions of years. In the dense environment of a galaxy cluster, galaxies are constantly interacting, drawn together by gravity and slowly merging into larger systems. Each time two galaxies collide, their stars, gas, and dark matter blend into a new, more massive structure. Over cosmic time, IC 1101 grew by devouring smaller galaxies, one after another, in a process astronomers sometimes call galactic cannibalism. The galaxy's enormous mass and luminosity are the accumulated result of these ancient mergers, each one a chapter in a long, slow saga of growth. The process of forming such a galaxy is violent yet beautiful. When two galaxies merge, their gravitational fields twist and distort one another, creating long tails of stars that stretch across space. Gas clouds collide and compress, triggering short-lived bursts of star formation, while supermassive black holes at their centers spiral toward each other, eventually merging into even more massive singularities. Over time, the distinctive spiral or irregular shapes of the original galaxies fade, replaced by the smooth, featureless structure of an elliptical giant. The result is a vast, spheroidal galaxy filled with stars that have been scattered into random orbits. The spiral arms and disks that once gave structure are lost, replaced by the calm uniformity of a gravitational equilibrium that has settled after billions of years of cosmic turbulence. The heart of IC 1101 lies a supermassive black hole, one of the largest known in the universe. Estimates suggest that its mass may be more than 40 billion times that of our Sun, perhaps even greater. This incomprehensible object anchors the galaxy, shaping its core and influencing its evolution. When IC 1101E's black hole was actively feeding on gas and dust billions of years ago, it would have been one of the brightest quasars in the universe. Today, it may be relatively dormant, having exhausted much of the nearby material, but even in its quiet state, its gravitational power continues to bind billions of stars in orbit, maintaining the galaxy's internal balance. IC 1101E's location within the Able 2029 cluster is another clue to its extraordinary nature. Galaxy clusters are the most massive gravitationally bound structures in the universe, containing thousands of galaxies, vast clouds of hot gas, and enormous reservoirs of dark matter. The central galaxy of such a cluster tends to grow disproportionately larger than the rest, feeding on the smaller galaxies that fall toward the cluster's core. IC 1101E's immense size and luminosity reflect its central position in this environment. It has had billions of years to absorb and accumulate matter from its neighbors. The faint outer halo of IC 1101 extends deep into the surrounding intra-cluster space, blending seamlessly into the background of stars that have been stripped from other galaxies. Its outermost regions are so diffuse that it becomes difficult to say where the galaxy ends and the cluster begins. The color of IC 1101 tells another part of its story. Observations show that it has a yellowish hue, an indication of an old stellar population. Most of its stars are ancient, born in the early universe, and now slowly aging. The galaxy's supply of cold gas, the raw material needed to form new stars, has been largely exhausted or heated to such high temperatures that it can no longer condense. As a result, IC 1101 is a galaxy in quiet retirement. It glows not with the fierce blue fire of youth, but with the steady, golden light of maturity. Yet despite this stillness, its mass continues to grow subtly as it draws in smaller galaxies and loose material from its surroundings. Astronomers studying IC 1101 often describe it as a relic of the universe's most dynamic era. In the early cosmic epochs, when galaxies were forming at a rapid pace, collisions were common. Over time, as the universe expanded and galaxies moved farther apart, these collisions became less frequent. IC 1101 is a survivor of that earlier time, a record of the era when gravity sculpted the largest galactic structures through endless mergers. Its sheer size suggests that the Able 2029 cluster has existed for billions of years, providing a stable environment for IC 1101 to grow. The galaxy's light, now reaching us after a billion-year journey, offers a window into that ancient cosmic landscape. Even though IC 1101 is the largest known galaxy, it may not be the largest that exists. The observable universe is limited by the speed of light. There may be galaxies beyond our observational reach that are even larger. Moreover, as astronomers develop more powerful telescopes and instruments, they continue to discover new cosmic giants, some with radiolobes extending for tens of millions of light years, others with central black holes of unimaginable size. Yet IC 1101 remains the benchmark, a symbol of what gravity can achieve when given enough time and material. The scale of IC 1101 forces us to rethink our sense of proportion. The Milky Way, which feels infinite when viewed from within, would be but a small component if placed inside this massive elliptical. Hundreds of Milky Way-sized galaxies could fit within its boundaries. If our solar system were located in IC 1101, it would orbit a galaxy whose night sky would glow far brighter than ours, illuminated by the diffuse light of trillions of ancient stars. The galactic core would dominate the heavens, not as a faint band of light, but as a glowing, golden mist stretching across the entire sky. The very concept of distance would lose its familiar meaning within such immensity. What makes IC 1101 so compelling is not only its size, but its quietness. Despite containing 100 trillion stars and an enormous black hole, it moves through the universe in profound silence. Its light, stretched across millions of light years, fades softly into the darkness, a golden ghost of cosmic history. Every star within it contributes to the collective radiance of an object that has existed for billions of years, an ancient monument built by the slow work of gravity. When we observe it, we are seeing not just a galaxy, but a time capsule from a younger universe, a vast and distant mirror reflecting the forces that shaped everything we know. IC 1101 stands as a testament to the scale and patience of the cosmos. It embodies the quiet grandeur of galactic evolution, the power of gravity to sculpt beauty from chaos, and the inevitability of growth and decay written into the universe's design. It reminds us that even in a universe that spans trillions of light years, there are structures so vast that they challenge the boundaries of our imagination, inviting us to gaze deeper, to wonder longer, and to realize how small, yet how fortunate we are to be part of a cosmos capable of creating something so endlessly magnificent. When we look up at the night sky, it's easy to forget that every pinpoint of light we see belongs to an immense structure, the Milky Way galaxy, our cosmic home. It is a sprawling, spiral-shaped system containing hundreds of billions of stars, planets, nebulae, and an enormous halo of dark matter. For us, the Milky Way feels impossibly vast. It stretches about 100,000 light-years across and contains a central bulge, beautiful spiral arms, and a supermassive black hole named Sagittarius at its core. Yet when we compare it to galaxies like IC 1101, our Milky Way appears modest, even small. Understanding how the Milky Way measures up helps us appreciate both its beauty and its place in the grand architecture of the cosmos. The Milky Way is classified as a barred spiral galaxy. This means that its spiral arms, those luminous swirls of stars and gas that define its shape, extend from a central bar-shaped structure of stars that runs through its core. The bar itself spans roughly 27,000 light-years, and the entire disk of the galaxy is only about 1,000 light-years thick. Within this delicate disk, stars orbit the galactic center at incredible speeds, completing one full revolution roughly every 230 million years. That means since the time dinosaurs roamed Earth, the solar system has completed just one orbit of the Milky Way. The sheer timescales involved already feel unimaginable, yet they are a mere heartbeat compared to the galaxy's total age of over 13 billion years. The Milky Way's population of stars is estimated between 200 billion and 400 billion. Most of these stars are concentrated in the galactic disk, where gas and dust continue to fuel new star formation. This gives the Milky Way its characteristic blue-white glow in astronomical images, a sign of ongoing stellar birth. Young, hot stars dominate the spiral arms, while older, redder stars inhabit the bulge and halo. The galaxy's spiral arms are not fixed structures. They are density waves, like ripples in a pond, where gas and dust temporarily compress to form clusters of newborn stars. As the stars age and move on, new waves form, perpetuating this cosmic cycle of creation and renewal. At the very heart of our galaxy lies Sagittarius A, a supermassive black hole with a mass roughly 4.3 million times that of the Sun. It sits quietly, about 26,000 light-years from Earth, surrounded by a dense region of stars, dust, and gas. In comparison to the monstrous black hole of IC 1101, Sagittarius A seems almost tiny. The difference in scale is staggering. The black hole at the center of IC May 1101 weigh tens of billions of solar masses, while ours is only in the millions. Yet Sagittarius A still exerts a profound influence on the structure of our galaxy. Stars near the galactic core orbit it at blistering speeds, revealing its immense gravitational pull. Occasionally, a passing star or cloud of gas wanders too close, gets torn apart, and briefly ignites the black hole's surroundings in a flare of X-rays, a glimpse of the tremendous power lurking in our galaxy's quiet heart. In cosmic terms, the Milky Way is a medium-sized galaxy, but it's far from insignificant. It belongs to a local family of galaxies known as the local group, which includes about 80 galaxies bound together by gravity. The two largest are the Milky Way and the Andromeda Galaxy M31, which is slightly bigger, measuring about 220,000 light-years across. Andromeda contains perhaps 1 trillion stars, about twice as many as our own galaxy. The two are on a slow-motion collision course, set to merge in roughly 4 to 5 billion years. When that happens, the Milky Way and Andromeda will coalesce into a single elliptical galaxy, possibly similar in appearance to IC 1101, though much smaller. That future merger reminds us that the processes that built IC 1101 are not unique, they are universal and ongoing. Even our quiet corner of space will one day host a grand galactic union. If we compare the Milky Way to IC 1101 directly, the difference is almost beyond comprehension. IC 1101E's diameter exceeds 5.5 million light-years, while the Milky Way's is just 100,000. You could line up more than 50 Milky Ways across the span of IC 1101, and still, there would be room to spare. In terms of stellar population, Our galaxy has a few 100 billion stars, while IC 1101 holds up to 100 trillion. That's a difference of nearly 3 orders of magnitude. The Milky Way's total mass, including stars, gas, dust, and dark matter, is estimated at around 122 trillion solar masses, while IC May 1101 contain up to 100 trillion solar masses. The comparison is almost absurd, like comparing a city to a continent. Yet, despite its smaller size, the Milky Way is far more structured and vibrant than a giant elliptical like IC 1101. While IC 1101 glows faintly with the diffuse light of old, dying stars, the Milky Way still bursts with color and life. Its spiral arms are nurseries for new stars, filled with vast clouds of gas and dust, where gravity continues to sculpt new suns and planets. The Orion Arm, where our solar system resides, is one such region, a modest spur between the Sagittarius and Perseus arms, yet rich in nebulae and open clusters. The Eagle Nebula, the Carina Nebula, and the Lagoon Nebula are just a few examples of regions where stars are currently being born, their young light illuminating the surrounding clouds in vibrant shades of red and blue. This ongoing cycle of star formation gives the Milky Way a kind of cosmic youthfulness. In contrast, IC 1101 is an ancient, quiescent galaxy whose star-making days ended billions of years ago. The Milky Way's spiral structure ensures that fresh material continues to circulate through the disk, providing the raw ingredients for new generations of stars. Its interstellar medium, a mix of hydrogen, helium, and trace elements, serves as the galaxy's lifeblood, continually recycled by supernova explosions that both destroy and create. Every massive star that dies in a supernova returns heavy elements like carbon, oxygen, and iron to the galaxy, enriching the next generation of stars and planets. It is this cosmic recycling that makes life possible, not just on Earth, but potentially across other worlds in our galaxy. From another perspective, the Milky Way's relatively smaller size could even be an advantage. Its spiral structure and active star-forming regions create diversity, regions of calm and chaos, light and darkness. In such an environment, planetary systems can form and evolve under a wide range of conditions. The Milky Way is also less dense than the core of IC 1101, meaning stars are spaced far enough apart for planets like ours to exist safely, without being constantly bombarded by nearby supernova or gravitational disturbances. Our position, about halfway from the galactic center to the edge, provides both safety and stability, a perfect perch from which to observe the universe. The Milky Way's halo extends far beyond its visible disk, encompassing not just stars, but ancient globular clusters and an immense envelope of dark matter. This dark matter, invisible yet dominant, accounts for most of the galaxy's mass and exerts a gravitational influence that holds the galaxy together. Without it, the Milky Way's rotation would fling stars into space. Astronomers have mapped this unseen halo through the motions of distant stars and satellite galaxies, discovering that it may extend several 100,000 light-years in every direction. This invisible structure connects our galaxy to the larger cosmic web, where filaments of dark matter thread through the universe like an interstellar scaffold. When we think about how the Milky Way measures up, it's not just about size, it's also about character. The Milky Way is dynamic, evolving, and filled with energy. IC May 1101 dwarf it in scale, but our galaxy tells a story of balance and renewal. It is a place where gravity and motion, chaos and order come together to create the conditions for life. The Milky Way's spiral arms are like the veins of a living organism, constantly circulating material and light. Its stars range from brilliant young blue giants to quiet red dwarfs, from dense neutron stars to black holes scattered through its disk. Each one plays a role in the grand symphony of cosmic evolution. The Milky Way's influence extends far beyond its visible borders. Dozens of smaller satellite galaxies orbit it, including the Magellanic Cloud's 2 irregular dwarf galaxies visible from the southern hemisphere. These satellites are slowly being drawn in by our galaxy's gravity, their stars and gas gradually stripped away to form long tidal streams. This process mirrors the same gravitational interactions that once built giants like IC 1101, only on a smaller scale. Over the next few billion years, the Milky Way will continue to grow by absorbing its companions, inching closer toward the fate that awaits it with Andromeda. If we could view the Milky Way from outside, from a vantage point millions of light years away, we would see a magnificent spiral glowing against the dark tapestry of the universe. Its bright core would shimmer like a pearl, its arms coiling gracefully outward, dotted with clusters of blue-white light and streaks of dark dust. In the vast cosmic hierarchy, it might not rank among the giants, but it would stand out for its beauty and complexity, a masterpiece of motion and light, born from billions of years of cosmic evolution. In the end, when we compare the Milky Way to the colossal IC 1101, we find a story not of inferiority, but of diversity. The universe builds galaxies of all kinds: tiny dwarfs, sprawling spirals, and enormous ellipticals. The Milky Way, with its spiraling arms, dynamic structure, and ongoing star birth, represents one of the most intricate and life-friendly designs among them. It may not be the biggest, but it's alive in ways that IC 1101 no longer is. Its stars still ignite, its planets still form, and its cycles still continue, a living galaxy in a universe filled with ancient, fading giants. Galaxies are not static islands of stars, they are living, evolving systems shaped by gravity, time, and cosmic circumstance. From the smallest dwarf galaxies to the titans like IC 1101, each one tells the story of how the universe organizes matter on the grandest scales. The question of why galaxies grow so huge, why some reach millions of light years across while others remain small and faint, is a story that stretches across the entire history of the cosmos. It involves the invisible scaffolding of dark matter, the violent interactions between galaxies, the quiet accumulation of gas, and the relentless pull of gravity that never rests. To understand why galaxies can become so enormous, we must first travel back to the beginning, the moment when galaxies were born. Shortly after the Big Bang, about 13.8 billion years ago, the universe was a hot, dense soup of particles. As it expanded and cooled, matter began to clump together under the influence of gravity, forming the first dark matter halos, regions of invisible mass that served as the seeds of galaxies. Ordinary matter, made of protons and electrons, fell into these halos and began to form gas clouds, which eventually condensed into the first stars. These earliest galaxies were small and irregular, often just a few thousand light years across. They were chaotic, filled with violent star formation and supernova explosions that blew gas out into space. Yet these humble beginnings set the stage for everything that followed. Over billions of years, gravity continued its patient work, pulling galaxies toward one another. When galaxies collide, they do not crash like solid objects. Instead, their stars pass by mostly unharmed, while their gas and dust interact violently, triggering bursts of star formation. Each merger reshapes the galaxies involved, transforming small spirals into larger ellipticals, feeding central black holes and redistributing stars. This process, galactic merging, is one of the primary ways galaxies grow. The more massive a galaxy becomes, the stronger its gravitational pull, allowing it to attract even more material. Over cosmic time, this runaway process leads to the formation of enormous galaxies like IC 1101, which have consumed dozens or even hundreds of smaller companions. But merging alone does not tell the whole story. The environment in which a galaxy lives plays a crucial role in determining its ultimate size. Galaxies in dense regions of the universe, such as galaxy clusters, are far more likely to grow into giants than those in isolation. In these clusters, thousands of galaxies orbit within a relatively small region of space, their mutual gravity constantly drawing them together. The central galaxy of such a cluster, called a seedy galaxy, often becomes a cosmic behemoth through the repeated accretion of its neighbors. IC1101, for example, sits at the center of the Able 2029 cluster, surrounded by a swarm of smaller galaxies that it has been consuming for billions of years. The dense environment acts like a feeding ground, providing a constant supply of material to sustain the giant's growth. Another key factor is the mysterious presence of dark matter. Although invisible, dark matter makes up roughly 85% of all matter in the universe. It forms vast halos around galaxies, extending far beyond their visible edges. These halos are the true gravitational engines of galactic formation and growth. The more massive a galaxy's dark matter halo, the more gas and smaller galaxies it can attract. In regions where dark matter halos are particularly large and dense, galaxies have the potential to grow to extraordinary sizes. In this sense, the size of a galaxy like IC1101 is not only the result of visible stars and gas, but of an invisible structure of unimaginable mass that has been accumulating matter since the dawn of time. Gas accretion, the slow inflow of intergalactic gas, is another mechanism that fuels galactic growth. Even after the early period of galaxy formation, vast streams of hydrogen continue to flow along the cosmic web, the enormous network of filaments that connects galaxies across the universe. These streams act as lifelines, feeding galaxies with the raw material for new stars. In smaller galaxies like the Milky Way, this inflow keeps star formation alive, ensuring that new stars continue to form in the spiral arms. In massive ellipticals, however, the situation is different. Their enormous gravity heats incoming gas to millions of degrees, preventing it from cooling and forming new stars. Instead, this gas settles into a hot halo that surrounds the galaxy, contributing to its overall mass, but not to its luminosity. Thus, the largest galaxies often appear faint and reddish, not because they lack matter, but because their matter is locked in forms that no longer shine. Supermassive black holes also play a subtle yet profound role in galactic growth. At the center of nearly every large galaxy lies one of these gravitational monsters, with masses ranging from millions to billions of suns. As galaxies merge, their central black holes eventually spiral toward each other and combine, growing even larger. These black holes exert a strong influence on their surroundings. When actively feeding, they emit enormous amounts of energy, blowing gas and dust out into space in powerful jets. This feedback process can regulate star formation, preventing a galaxy from forming too many new stars too quickly. Ironically, while black holes help galaxies grow by merging, they also keep that growth in check by limiting how efficiently gas turns into stars. This delicate balance between accumulation and regulation shapes the final size and character of a galaxy. Cosmic time is perhaps the most important ingredient of all. The largest galaxies in the universe are also the oldest. They have had billions of years to merge, absorb, and accrete material. Each collision takes hundreds of millions of years to complete, and the resulting galaxy takes even longer to settle into equilibrium. IC1101, for instance, did not become a giant overnight. Its growth was the cumulative result of countless smaller events stretching back nearly the entire history of the universe. The fact that it exists at all tells us that it formed in a region of space where galaxies were numerous. Dark matter was abundant, and time was long enough for gravity to do its slow, persistent work. We can think of the process of galactic growth as a cosmic version of natural selection. In the early universe, small galaxies were abundant, but only those in the right environments could grow into giants. Galaxies in dense clusters interacted more frequently, leading to rapid growth through mergers. Those in isolation, like many dwarf galaxies near the edges of the universe, remained small and faint. Over time, the population of galaxies diversified. Some grew to massive ellipticals, others retained their spiral shapes. The universe, in its expansion, gradually slowed the rate of mergers, meaning that the era of giant galaxy formation has largely ended. Today, the largest galaxies we see are the remnants of a more chaotic, crowded universe that once teemed with collisions, Galactic cannibalism, where larger galaxies consume smaller ones, is still happening even now. Astronomers observing the Milky Way have detected several streams of stars stretching across the sky, the remnants of dwarf galaxies that our galaxy has already devoured. The Sagittarius dwarf galaxy, for example, is currently being torn apart by our galaxy's gravity, its stars spread across the Milky Way's halo. This ongoing process mirrors, on a smaller scale, what built the colossal galaxies at the centers of clusters. Over billions of years, these slow but steady feasts create massive ellipticals whose stars come from dozens of different ancestral galaxies. Another factor influencing galactic growth is the behavior of dark energy, the mysterious force driving the accelerated expansion of the universe. In the early universe, galaxies were much closer together, making mergers more common. But as dark energy began to dominate the cosmos, it pushed galaxies farther apart, reducing the rate of collisions. This means that the era of rapid galactic growth is effectively over. The largest galaxies we observe today, like IC 1101, represent the peak of this evolutionary process. In the far future, as the universe continues to expand, new mergers will become exceedingly rare, and galaxies will remain isolated, aging quietly in the vast darkness. In knowing this, we begin to see that the Milky Way's position in the universe is not random, but remarkably fortunate. Conclusion: our galactic perspective in the infinite universe, our journey through the cosmos, draws to a close. We are left with the profound realization about who we are, where we live, and what it means to exist in this vast universe. The Milky Way, our home galaxy, once seemed like the very center of creation. But as science peeled back the layers of the night sky, we discovered that our galaxy is but one among trillions, a mid-sized spiral adrift in the boundless sea of space. Compared to titans like IC 1101 or Hercules A, the Milky Way may appear modest, yet it holds something extraordinary. The observers capable of understanding it all, through the quiet beauty of spiral arms and the glowing halo of ancient stars. Our galaxy tells a story of balance and endurance. It is not the largest nor the smallest, not the brightest nor the faintest, but it exists in a region of cosmic calm, an environment where stars can live long, where planets can form, and where intelligent life can evolve and reflect on the wonder of its surroundings. The giants of the universe may outshine us in size, but not in significance. For what they possess in mass and brilliance, we balance with awareness, curiosity, and imagination. From the earliest star-forming clouds to the gravitational majesty of superclusters, everything in the universe follows the same grand design. Galaxies form, grow, collide, and transform. Stars are born, shine, and die, scattering the elements of life into the darkness. And across billions of years, gravity weaves everything together into a delicate cosmic web, a structure so immense that it challenges the limits of human comprehension. Yet here we are, small beings on a small world, capable of tracing that web across the sky and finding meaning within it. When we gaze up at the Milky Way, we are not just looking at stars, we are looking at our home, our origin, and our connection to everything that exists. The same forces that shaped IC 1101E's colossal form shaped our galaxy, too. The same cosmic dance that forged clusters and filaments gave rise to the sun, Earth, and to every living thing that breathes beneath its light. We are not separate from the cosmos. We are its consciousness, the universe becoming aware of itself. So, as we drift through the quiet of night, let us remember that our galaxy, though dwarfed by others, holds a kind of greatness that cannot be measured in light years. It is the greatness of perspective, the ability to look beyond, to ask questions, and to marvel at what lies beyond our reach. The Milky Way is our ship in the cosmic ocean, and while we may never touch the shores of the largest galaxies, our minds have already traveled farther than any starship ever could. In the stillness between the stars, science becomes poetry, a whisper reminding us that in every particle of dust, every flicker of starlight, and every distant galaxy, there is a shared origin and a shared destiny. The universe is vast beyond measure, yet within that vastness, we have found our place, a small, shining home among giants.